we go. All right. And we're off. Okay. So what's the plot for today? So today we're going to be talking about subspaces, which, as I already hinted at, is just a vector space hidden within another vector space. So let's start off with a nice and instructive example motivating the definition, and then we'll get into the good stuff. So in your mind, think about what R2 looks like for a moment, right? The collection of ordered lists of two real numbers. So pictorially, this is right, the Euclidean plane, just points in the space, right? There's an x coordinate giving me the left and right movement, and there's a y coordinate giving me the up and down movement. All right. Well, let's look at a subset, right? Because a subspace, as we will see, is a vector space within another one. So let's look at this set. So this is the collection of elements in R2, where I'm denoting their the first entry by x and the second entry by y, that satisfy the following equation. So here, note, I'm creating this subset of R2 using set builder notation. So if you're not super familiar, on the left is, here are the things in the set, and then on the right of the colon is the property they satisfy. Some people use a different notation. Instead of a colon here, they'll use a vertical line. I'm more of a fan of using the colon, but you might see a different notation. But essentially, on the left, the sets, the elements in question, and on the right, the property that they're satisfying. So if you stare at this property they're satisfying, this is requiring twice the first coordinate minus the second coordinate equaling 0. If you solve that equation, that gives me y is equal to 2x. So in other words, this is just simply the graph of the function y equals 2x. If we think about what that looks like, well, that's a line going through the origin. And a line in R2, well, that just looks like the real line, right? Specifically y equals 2x. It's just the real line, but it's been rotated, it's been tilted. But it's still the real line. So it looks like the real line, just rotated in a different setting. And what do we know about that? Well, we know that set is a vector space. So our feeling should be that this subset is a vector space itself. Now, in order to be a vector space, you need a scaling and an addition. Right now, rather than creating brand new scalings and additions, R2 has scaling and addition. So let's see how that affects the set M. Okay. So we'll investigate a little bit more closely and specifically with respect to scaling. All right, before we get too nuts, though, let's note that my set M has stuff in it. Particularly, it's got the vector 0, 0 in it, right? Again, the line y equals 2x, let those go through the origin, so the point 0, 0 is in there. So it's got stuff in there. Now let's see how scaling affects the set. Now, before we do any proofs, we can envision in our head, if you are on a line and we scale, remember scaling in R2 stretches, compresses, or flips in the opposite direction. If you're on a line and you do this, you'll remain on the same line. And so here we can see it being more formally demonstrated. So anything out of M has to satisfy this equation. So if we take a point x, it's an M. Again, using a bold here to represent elements at R2, well, its first coordinate times 2 minus its second coordinate needs to equal 0. Right? If you're in the set, that means you have this property. Okay. Now, if I take this equation and I scale it by alpha, I can arrange the alpha on the left-hand side to make it look a little bit nicer. 0 times alpha is 0, so it doesn't show up on the right-hand side. But now note, alpha x1, alpha x2, that satisfies the equation, so alpha x must be an element of M. So the scaling operation from R2 is closed with respect to M. So scaling anything in M keeps us in M. So remember, the way a scaling is defined in a vector space, it says, give me a real number and an element of the vector space. I'll create something in the vector space that satisfies some properties. So here we see in M, taking anything in M, we can define a scaling of it that keeps us within M. All right, let's keep going. So take two elements, x and y. They'll have to satisfy the equations, right? If you're in the set, you satisfy this property. So I've got these two equations, adding them together, 0 plus 0 is 0. And factoring out the 2's and rearranging everything. Here we see the first coordinates added together, the second coordinates added together, and they satisfy the required equation to be in the set. So their summation will belong to M. This one's a little trickier to imagine if you've got 2 points on the same line and adding them together keeps you on the same line. Well, obviously, if they're in the same direction, adding them will shoot you in the same direction. If they're in opposite directions, that's the one where you kind of have to go like, well, they'll either go in the negative direction, or they'll go in the other one. They'll still remain on the line. That's one's a little trickier to see, but algebraically, it comes out real nice. Right. So the set M is a subset of R2. R2 is a vector space with the scaling and addition operations. It's got stuff in it. The scaling keeps you in the set. So we have access to the mapping that takes a real number and an element from M and maps it to M. And we have access to the mapping that takes two things from M, and when you add it together, it also keeps us in M. So rather than creating brand new vector space operations on M, the previous ones that we created are conservative over the set, right? They're closed. So scaling doesn't escape the set, neither does adding. So feels like, equipped with those operations, M becomes a vector space in its own right. Okay. So that's our goal. Let's formalize that and set it up. So the idea of a subspace then is a subset in a vector space that becomes a vector space, and the conditions, the requirements for that are exactly the three things we saw from the previous example. The set itself is non-empty, scaling elements of the set do not escape the set, and adding elements of the set do not escape the set. So, in other words, if we restrict the inputs to M, the outputs will remain in M. Okay. So every time we talk subspace, right, again, of course, the vector space is an abstract object that just has stuff in it, equipped with operations that do what we want to. We don't particularly care about what the stuff are or what the just lost train of thought. We don't care what the operations themselves do, just that they satisfy the conditions we want them to. So, subspace then, subset of V, is we're going to now prove this becomes a vector space itself, taking the operations from V and restricting their inputs to only things out of M. Right. So these two axioms right here for requirements for being a subspace, this tells us that those are well-defined operations on M, right? Because I can talk about scaling something and I can talk about adding things that belong to M, right? The scaling and the summation do not jump outside of the set. Right. So this is what we want to prove. So what does that mean? That means that we need to verify that these operations check off all 8 boxes for the requirement of being a vector space. Now, before we do that, it will behoove us to actually prove some basic properties of subspaces. In particular, let's make the proof of this proposition go pretty smoothly. All right. So, we're going to prove some stuff about subspaces. So in particular, note the definition required that the subspace was a non-empty set. We're now going to prove that we can actually do a little bit better. Specifically, the additive identity of the vector space has to be in M. Right, so we explicitly verified that with the example we looked at in R2. Right, and again, whenever we're thinking about this and you're going like, okay, it's getting too abstract, just go back to that example. It's the plane, subspaces, lines going for the origin. Okay. All right. Now, the definition for a subspace that we're using says you have to be non-empty. There are these like weirdo examples where it's not immediately obvious that the additive identity is in there, but there's this other thing that you know is in there. and then you can force the zero, the additive identity, to be in there. So it's a more broad definition, so it's a little bit nicer. But in practice, you almost always start off by verifying that the additive identity of the vector space is in there. There are like the occasional ones where it's not quite clear and kind of in retrospect it's obvious sort of deal. So we'll prove that first. Then the next thing we'll prove is that anything that is in the vector space, its additive inverse is also there as well, right? And we're going to need to prove this because what we want to prove is that any subspace becomes a vector space in its own right. So it needs to have additive inverses. So rather than creating brand new ones, let's just use the ones we already know exist, right? And likewise right here, rather than creating a brand new additive identity, well, let's just use the one that we already have. And the last thing we'll prove is that with respect to any number of scaling and adding, we have to belong to the subspace. So any number of things in the subspace, scaling and adding them up does not jump you out of the subspace. Another way of saying this is that every linear combination of elements of the subspace are in there, right? And again, we discussed when we're talking linear in mathematics, we're talking scaling and adding. All right, cool. And part C will actually be our first proof by induction. So it'll be a good time. All right. So let's do some proofs. Now, all three of these are pretty nice, easy proofs, but as always, easy proofs are very instructive, so they're worth doing. All right, so since we're not empty, that means we've got something in the set. Call it X. Doesn't matter, then we just know there's something in there. Now, what do we know about scaling by zero? Scaling by zero will give us the additive identity, 0 sub v. And since M is a subspace, scaling, I don't care what you scale by, will keep you in the set. So, boom, proof's over. Nice and easy, right? And note, we've used explicitly quite a few of our assumptions, right? M is a subspace, so it's non-empty. Non-empty, and it's closed under scaling. The only thing we didn't use is that it's closed under addition. But we've used we used hypotheses. Basically, so we used hypotheses we made. That's always a good red flag if you're reading a proof and you're not sure about what's going on. If hypotheses that were stated are not being used, something might be wrong. Or the hypotheses might be overkill. That happens sometimes too. Right. So part A, nice and easy. Let's go to part B. All right. Well, very similar to the previous one. Scaling by -1 gives us the additive inverse. We didn't explicitly prove this, but it's in the type notes that are available on Canvas. So there you go. So if you're in the set, so is its additive inverse. It's nice. And again, just from the scaling, we get this. All right. So now for C. All right. So C is actually going to be our first example of a proof by induction. So pretty good stuff. All right. And of course, by a proof by induction, we get to start off. I always love starting off, go like, we're going to proceed inductively. It really makes it sound like you're doing something way more advanced than you actually are. So similar in the type notes, there's a spot where I say we're going to proceed by contraposition or contrapositively. That makes it sound really cool. So before we get to this proof, I've got a couple things about induction I want to talk about. So in the event you don't know, so over in VetMed here at Iowa State, induction, I guess, is like a procedure that they do. And so there's a room called the induction recovery room. So if you want to, if this is too much for you today, you need to head over there. And then secondly, when it comes to induction, potentially the way that you were taught it was kind of like maybe a very rigorous sort of, okay, write base case, and then write induction hypothesis, and then write the proof. And when you're first learning proofs, that's great. You kind of want to get into that to get a good feel for it. But, right, like, no professional mathematician writes an induction proof that way. Right, we just write it as follows. So, okay, base case, when n equals 1, well, yep, x sub 1 is an m, scale it, you're in there. Boom, that's it. Okay, now for induction hypothesis, suppose it worked for some m, I'm now going to verify that it works for m plus 1. So suppose that you could add up m number of things and scale it, and it remains in m. Well, if we go to m plus 1, well, that summation is just the m summation plus the term that's missing. M is a subspace. This is in the set. This is also in the set because scaling x sub m plus 1 by alpha m plus 1 will remain in the set, and it's closed under addition, so when you add them together, you're in there as well. And then the induction proof is over. There we go. For any n, this will work now, right? Because I proved it's good for n equals 1, and if you know it's good for m, I could verify that it's true for m plus 1. So you can think of it kind of like a domino effect. When I set up my dominoes, one falls over, it definitely, and it will knock over the next one, and there is a domino that works, so it will infinitely knock over and be good. All right. And of course, another way of thinking of it is you're trying to prove something is true for any n. Well, if it's true for 1, and then true for anything following where you're given space, that means you know it's true for 1, and then you know it's true for 2, and thus it's true for 3, and 4, and 5, and 6, and so forth. All right, so like I just demonstrated, I like writing induction a little more free flowy than like explicitly going base case, induction hypothesis, so on and so forth. I hated that when I first learned it in my proofs class, and I always deliberately didn't write that way and lost points because I vehemently disagreed. But Professor Alakim was not a fan of that, so he just took points off. In my undergrad proof class, he was also my undergrad advisor. Yeah, he took me aside once and said, you shouldn't be a math major. Joke's on him. So anyway, yeah. So I always wrote induction pretty loosely like this. I felt when we were like learning it and it was like being really restrictive. I'm like, this is like those garbage geometry proofs we did in high school. I don't want we're beyond that. So I like this way. If you do want to write it out very explicitly when we do induction proofs, go ahead. That's fine. Nothing wrong with it. I like writing it this way. And yeah. Okay, so without going further off the deep end here, let's move on. All right, so as promised, every subspace of a vector space becomes a vector space in its own right by taking the scaling and addition we already have access to and simply applying it to M. Now, since you're a subspace, that means scaling and adding keeps you within M, so those operations exist. We just need to now verify that it satisfies the 8 conditions in order to be a vector space. And for addition, the associativity and the commutativity, we don't have to do anything. This is just baked into the addition for V, right? By how it works for adding elements of V, take anything out of M, well, everything in M is in V, so it'll just satisfy this. We don't have to do anything. I mean, for the most part, almost all of this proof is just like boring. It's like super just like bookkeeping. It's really not the most exciting proof. But it's important. It gives us a way of talking about vector spaces constructed from old ones. You can make new ones by starting off with a vector space and then identifying a subspace within it. So the associativity works, the commutativity works. As we prove, the additive identity is in M, and thus it will become the additive identity of M with respect to addition. Right? So rather than trying to create a new one, just use the old one. We just need to make sure it's actually in the set, which we already proved. Okay, so the addition is associative, it's commutative, it's got an identity. Now we just need to verify that it has inverses, and boom, it does. Because as we proved, anything that's in the subspace, its additive inverse remains in the set. And by construction, it satisfies the requirement we need, it adds up to the identity, and as we verified, that identity lives in M. So within M, we have access to inverses. And again, rather than creating brand new ones, just use the ones we already have. Okay, so the 4 main addition axioms, easily checked off, they all work. So what's left? All the scaling axioms, and all of the scaling axioms are even more boring because, again, the scaling, we're taking it from V. It already satisfies everything for elements of V, so it will satisfy all of them for elements of M, because M is contained in V, so they're elements of V. So distributivity works the way we want it to. The conversion of the addition of the reals to the addition of the vector space works the way we want it to. The conversion of multiplication to scaling works. And scaling by 1 doesn't do anything new. X is in M, which means it came out of E, so scaling it by 1 doesn't do anything. All right. So in reality, the only steps here that we actually had to do a little bit of work was was 3 and 4. Right, 3 is M, but you like rotated it and rounded it out. That's where my brain went. Right, they were the only ones where we actually do a little bit of work, so we had to verify that indeed the additive identity was an element of M, and any of the additive inverses do not escape M. So all the other ones are just for free. They're just automatic. They're built into the assumptions of V being a vector space. And boom, there we go. Subspaces are precisely the entities within vector spaces that become vector spaces themselves. Cool. All right. So, we got that stated. Do a Coke Zero break. So this morning's lecture, I was chugging coffee while I was doing it. So regardless, whenever I'm doing math, just inject that caffeine right into me, man. I might have a problem. Anyway. All right. So now that we got that, let's actually use this to create a new vector space. Right? This tells me that I can form vector spaces if I start with a vector space to begin with and look for certain subsets. And in practice, this is usually how you create new vector spaces. You start off with a larger construct that you're interested in, and then you focus in on certain subspaces. So we've got a vector space that we like. Other than Rn, we can also talk about the set of polynomials. Right? So again, our notation for that is R square brackets X, which is a pretty standard notation. I do want to note that our textbook uses a different notation. It uses just like P, which is prevalent as well. I've also seen capital Pi used for polynomials. There's a lot of people get all creative with that. So I'm going to use that notation. This is a pretty standard algebra notation for it. We are in linear algebra. All right, this is a vector space. It's closed under, when equipped with the scaling and the addition for functions. So specifically given a function, you can scale it by feeding in the input and then multiplying by the scalar. And right, we can define the addition of two functions by feeding in the inputs individually and adding them up. Right, now we didn't explicitly prove it, but as I noted in the typed up notes, you can verify that all 8 of the axioms needed for a vector space are easily verified, so go for the grueling work there if you're really interested. Now, let's fix a number that lives between 0, 1, 2, 3, and is an integer value. So in other words, the wrong natural numbers, the natural numbers including 0, we'll define R sub m, x, to be the polynomials that all have degree less than or equal to m. Now, this notation is a little less standard when it comes to the set of all polynomials whose degree has been restricted. There's no standard notation I've really seen for that. That's a Wild West crazy. Normally, the normal thing seems to be whatever you have for your polynomials, you just like indicate somewhere in the notation that you've got a degree restriction. And here I'm going to do sub m. Okay, so what does this specifically mean? This means that it consists of the functions that are polynomials, but we do not allow the coefficients to go beyond m. So the highest power we could possibly have is m itself. So as an example, I get a good feel of how this works. R2, for example, has 1 plus x squared. It will also have 1 plus x, right? Because the degree is less than or equal to 2. It's not explicitly equal to 2. So, right, note that this would still be of this form, but the C sub 2 is equal to 0. Oh, Charlotte is showing up.
Say hi.
Oh, hey, Charlie.
Hi.
Oh, no, the dogs are here, too. This is out of control.
Lily, Effie, go. Go. Go.
Right.
Hey,
Okay.
pop in. Pop
All
into
right,
Daddy's
so-
class. Say hi.
Are you going to show up, Charlie? We have a special guest appearance.
Say hi. Hi. All right, let's move along.
Okay.
We said hi. Let's go.
Okay, so right, so yeah, so the polynomials of so R sub 2 is the polynomials of degree less than or equal to 2, so stuff like this is in there, but you don't necessarily have to have x squared show up, but what you can't have show up are higher powers. So for example, x cubed would not be in this. All right, so surprise, this is a subspace of the set of polynomials. This shouldn't be too surprising. Now, the zero polynomial is in here. It is a polynomial of this form. You just make all of the coefficients equal to 0. Now, it's worth noting that when you talk degree, the zero polynomial, there is like a big debate as to what degree the zero polynomial should be given. Very similar to why we don't let 1 be a prime. Trying to put a degree to the zero polynomial basically ruins a whole bunch of theorems that are like degree specific. Particularly when you want to do like the degree of a product of two polynomials has a particular form to it. If you include the zero polynomial, it screws everything up. So the zero polynomial either is given no degree, or the more popular thing is to give it degree negative infinity, which is really dumb. But so that way, right, negative infinity is less than m, so it belongs to the set. It's really weird. So non-zero constants, there's no argument; those are given degree 0. But the zero polynomial, the zero function, it's like you can't give it a degree without having to make all sorts of like exceptions. So anyway, all right. Well, that belongs to the set. And now, in order to be a subspace, we need to verify closed under scaling and closed under addition. So scaling, obviously, if you look like this and you scale by alpha, well, then you just scale all the coefficients by alpha, and there you go. You still have the same form. And likewise, if you were to add two polynomials of this form, well, then you just add the coefficients together, and you're still of the same form. It is easily seen to be a subspace, and this is another classic example of subspace. Little harder to get a feel visually of, right? Because in R2, right, always think of just a line going for the origin when we're trying to envision the mathematician's realm, what this stuff looks like. But for this, it's a little harder to grasp. Now, before we move on, another classic example of a subspace is the following. This is one of my favorite examples of a subspace. So let's let M be the collection of all polynomials that have -1 as a root. So in other words, if I plug in -1 into the polynomial, I'll get 0. So visually, if you want to see what this looks like, imagine all of the possible polynomials, and the only requirement is that they go through the point -1, 0 in the R2 plane. Right, so all polynomials that you can think of that you can draw, and the only requirement is they go through the x-axis at the point -1. This set is indeed a subspace. So obviously the zero polynomial is in here because it spits out 0 for any input. So, right, the zero polynomial, again, is just the constant function 0. So that trivially satisfies this. If you take anything out of the set and scale it, well, you can't scale 0 by anything and get something non-zero, so any element of M scaled remains in M. And likewise, given any two elements P and Q, adding them together, well, they're both equal to 0 and -1, so that means they're equal to 0 and -1, their summation. So indeed, this is a subspace. Right, this is a cool example. I really like this one. This gives you a kind of a neat example of what subspaces can possibly be. This is actually a very specific example, too, of a more general thing that you look at. So like I mentioned, my field of research is functional analysis, which is this stuff plus calculus. So it's like this kind of material and then taking limits on top of that. And these sorts of sets, these are called kernels of point evaluators. So it's a very specific example. And those are super important and super useful. You can do all sorts of cool stuff with them. So, fun example. This is some neat stuff. Again, there's some deep lore math there. But all right. Okay, so that being said, let us now note that in order to prove something as a subspace, as we just had to do, we had to check three things. Check for non-empty, and like I said, in practice, it usually means showing whatever the additive identity is in the set. Show that it's closed under scaling, and then show that it's closed under addition. Well, it turns out that we can kind of streamline this into just one condition, which is showing that the scaling and addition of any two things remains within the set. So rather than proving scaling and addition separately, do it at the same time. And that usually this just makes life a little bit easier. So this is just a nice tool to prove, so that we can then more easily verify that certain subsets are subspaces. That's going to be our goal. And let's note that it's an if and only if, which means we got two things to do. We got to prove that if M is a subspace, then it has this property. And then conversely, if you have this property, then you're a subspace. If and only ifs are great, right? Because it's saying that these are logically equivalent, so it's a useful tool. But I remember when I was first doing proofs, I always hated when I had to prove an if and only if. I'm like, right, it's really two problems. Come on, it's like twice the work. But normally, one of the directions in an if and only if is easy. And in fact, the first one is pretty easy. Suppose you have a subspace. What do I want to prove? Given alpha and beta out of the reals and any two things out of M, then this lives in there. So pick two scalars, pick two things out of M, and since M is a subspace, that means scaling them remains in the set, and then adding them together will remain in the set. And boom, forward direction has been proven. If you are a subspace, then you have this property. And now note, the non-emptiness here, right, is just really, as you're going to see, I'm not going to explicitly use it. It's implicitly there to guarantee that we're subspace in the reverse direction right here. So like I said, whenever assumptions are put in a proof, if they don't get used, that's like, hey, why did you assume that? So let's do the reverse direction now. So suppose that for any two scalars and any two elements of M, this remains in M. All right. So I now want to prove that M is closed under scaling and closed under addition. Now note, already assumed non-empty, like I just said, so I don't need to do anything there. I have already asserted the non-emptiness. So I want to prove that it's closed under scaling, which means I want to show that alpha x needs to be in there. So let's let alpha be a real and let x be out of M. I want to prove alpha x is in there. Now, what do I know? I know that a summation with scalars can get in there. So if I choose my beta accordingly and my y accordingly, I can get that alpha x is in there. And here's the slick move. X is assumed to be an M. Alpha minus 1 and 1 are real numbers. So we know, by assumption, this quantity right here needs to be an M. Alpha minus 1 plus 1, that's equal to alpha. Boom. Nice. So there you go. So this is a cool little move. Now it's worth noting that I picked one. Nothing special. Just you could have picked any scalar you wanted, and this proof works exactly like this. And there we go. Nice. Another way of tackling this, so I had this morning I did it a little differently. Another way of attacking this is using the non-empty hypothesis to explicitly verify that 0 is in the set, and then from there show that choosing y to be 0, then you get the same thing. But this is less work, so preferred. All right. So we now prove that M is closed under scaling, assumed non-empty, so the only thing left to do is prove that it's closed under addition. So pick two things, and I want to use, again, this hypothesis, so I need to choose my alpha and my beta accordingly. Well, pick one. Scaling by 1 doesn't change anything, so there we go. In the set. Wash your hands, walk away. That's it. Proof's done. All right. Killing it. Killing it, man. All right, let's keep going. All right, now equipped with this easier check for determining subspaces, we can quickly identify a couple of things that are subspaces themselves. So this gives us a much easier way of detecting subspaces, a more streamlined approach. So, more examples. Now, within any vector space, there are always guaranteed two subspaces that exist. There are always two that you have access to. And here they are. So these are usually referred to as like the trivial subspaces, or like the boring ones, basically. So as we're about to prove, obviously you're a subspace of yourself. Right, no, the definition didn't say you need to be like a proper subset. You could just be the whole set. And we'll also prove that the smallest possible subspace actually exists, which is just the thing that consists of the identity. So as I noted, as an example of a vector space, a really boring one, if you just look at the singleton consisting of the real number 0, that becomes a vector space, just equipped with the usual operations of scaling and adding. And note, hey, that works for anything beyond the real numbers. So let's now verify that this is a subspace. So the first thing I want to note is that it's clearly non-empty. It's got the additive identity in there. It's got itself 0v in there. Pick two scalars, pick two elements out of the set. Well, the two elements out of the set have to be the additive identity. And scaling those gives you the additive identity. Adding that to itself just gives you itself, which is an element of the set. So, boom, it is a subspace. It's non-empty. And we just use our new exciting theorem to verify that it has the scaling and adding conditions. So, it's a subspace. And that's it. Easy proof. In fact, even easier. So V needs to be a subspace because, well, it's definitely not empty. It's got the additive identity in it at least. And pick any two things out of it, any two scalars. The linear combination of those, by definition, is in the set. So there you go. All right. So these are like the extreme examples of subspaces, right? So when I was talking, when you set up a definition, you always want to kind of like look for what are the ridiculous cases, what are like the really far out there sort of things. And here we go. Two pretty basic examples of subspaces. All right. Moving right along, let's get some more examples. So let's get a more exciting example, a little bit more of an interesting one. So given any element, we can create a subspace, and in fact, it's the smallest subspace that contains the element. Right. So let us make that a little bit more explicit here in this proof. Let's say you take something out of V. If you look at this and realize that you take something out of V, and you look at this. So again, this is set builder notation. Here where I'm saying on the left are the sets of interest, and on the right, property they satisfy. So all the things that look like this, where we have required alpha to be a real number. This forms a subspace. So specifically, take any two scalars and take u and v out of here. All right, now note, the notation that I'm using within here, although I am using an alpha here, this in here is like a placeholder notation. If you're going to be like really like, if you'd be like a good, you're real stickler about it, you wouldn't use alpha here. You would like use a different symbol. But to me, it's like this lives in a vacuum. It's in the curly braces. It's in its own world. So I can use alpha over here. It's fine. Okay. So since u is in the set, that means it is some scalar times x. So use delta for this. And since v is in the set, it's some scalar, and I used gamma in this case. Okay. Now, what do I want to prove? Well, I want to prove that when I scale u by alpha and v by beta and add them together, I remain in the set. So that means I need the verifier of this form. And that shouldn't be too surprising that it works, because if you scale u by alpha, well, then you'll get alpha times delta x. You scale phi by beta, then you'll get beta gamma x, and then we could pull out all the scalings and additions to right there. So this summation right here is just x scaled by by these particular scalars. So, all right, and note that this set is obviously non-empty, so it definitely has the 0 vector in it. For example, if you were to scale by 0, 0 sub v would be in the set. All right. Now, the next thing that we're going to prove, part B, any subspace that has x, in fact, contains this set. And that shouldn't be too hard to see, because x is an M, any scalar multiple, by definition, would belong in it. And that's it. So therefore, this set is contained in M, as promised. So if we were to sort of recontextualize what's going on here, this is saying that for any element x, pick anything x in our set, we can create a subspace that's explicitly based off of it. And furthermore, this subspace has a really unique property. It's the smallest subspace within the vector space that contains the element x. So this subspace that's generated by x is the sort of the most efficient subspace, requiring that x is in there. I wonder if that's like super important, something we're going to talk about tomorrow when we talk about the span of set. Beats me. No idea. All right. Okay, man, I did not get this far this morning. Like I said, though, this morning was all full of technical difficulties and fun stuff, so we're doing pretty good. All right. So let's keep chugging along here. I got a couple more minutes. I got a couple more things to talk about. All right. So, as we've just discussed, any vector space is always in possession of subspaces. So, particularly, it will always have the subspace that consists of just the additive identity and the whole set itself. So then naturally you want to ask, well, are there any other possible subspaces that exist? Well, here's an example where the answer is no. So the real numbers, again, are a vector space in their own right, where addition is the usual addition and scaling is multiplication. It turns out that the only possibilities for a subspace are the trivial ones, either the set consisting of just 0 or the whole set itself. There's no in between. Right. And if we think visually, that makes a lot of sense, because as we were discussing, we're thinking about how things look in terms of subspaces. Subspaces, like we've already kind of built into our heads, as like, they're lines in a way. And that's a good intuition for R2. For R3 and beyond, they're not exactly lines. In R3, they end up being lines or planes, but we'll get into that a little bit more. For the real numbers, though, there's no interesting subspaces. They're all boring. So let's prove that. All right, now this is my favorite proof. Not this one particularly, but my favorite style of proof. Know what we're trying to prove? We're trying to prove that an OR statement is true. Okay. In mathematics, we use the inclusive OR, which means this statement is true as long as one of them is true. Now, in this particular case, obviously we can't have both of them being true, but right, the way OR works in mathematics, both of them might be true. We will allow that possibility. So in order to prove that an OR statement is true, you just need to verify that one of the two things are true. Right? If this said exactly one holds, then that's a different story. Then you need to verify that exactly one of them holds, which means you got two things to prove. But for a general OR statement, like this, if m was equal to just the set consisting of 0, then the proof's over, because one of them is true. It's an inclusive OR, so I only need to prove one of them is true. So if that's true, I'm done. Proof's over. So I can start the proof by saying, all right, well, don't assume this. So suppose it is not equal to 0. I will now verify that that forces this to be true. It's real slick. I love this sort of thing where it's like you're like really you're bending logic to your will in a way. So I like it. But all right. So what do we need to prove? This or statement is true. Okay, well, if this was true, the or statement is itself true, so let's go ahead and assume it's not. We will now verify that all of the real numbers belong to M, and thus M itself is the real numbers. So, by hypothesis then, 0 is in the set, right? It is a subspace. And because it's not equal to 0, that means there's something in there that itself is not equal to 0. So we've got access to a non-zero element. Now, the scaling of the real line is multiplication. This is non-zero, so we've got access to its reciprocal, and hopefully you see where this is going now. So take any real number, x is in M, so scaling it by r, which in this case is multiplying it by r, belongs to M, and we have access to 1 over x, and scaling that, well, that's the multiplication, so if you arrange it around, the x's knock out, multiply by 1, get r, so now we've proven that r is an element of M, so since M contains every real number, and it's a subset of real numbers itself, it must equal r, and boom. There are no interesting subspaces of the real line, only the trivial ones. And this is a great example, really stressing that when we look at R as a vector space, scaling is multiplication. Having that in your head, is very important, and I've got some very fun examples later on where you really exploit that sort of, not dichotomy or duality, you really exploit that fact. I can't think of a fancier way of saying it, but whatever. Anyway, boom, exactly, 2 o'clock. Nailed it. All right. So that is it for today. Tomorrow, so I got a couple more slides that I want to talk about, which will classify the subspaces of R2. So we'll prove that all the subspaces of R2 have to be lines or the trivial ones. And then we'll move into, as promised, 4.3, the span of a set. So we'll talk a little bit about that. No confirmation just yet, but most likely we will be online. I'll make an announcement letting you know. So we'll be doing this thing same time and in my basement once again. All right, that's it for today. Thank you for joining me. Had a good time. Hope you did too. I'll be posting this recorded lecture. So, all right, stop the recording.